I'm very excited. So this is my series on introduction to Python for physics people. I'm kind of assuming that you already know something about physics. Maybe you're physics faculty, maybe you're a physics student, but that's fine. How to use Python. And this is my favorite, best ever experiment to do. I've pre-recorded some videos so that I can use. Let me show you this one on the right. So right here I have a spring hanging on a wall, and there's a mass on there. No, this one I want to show you first. So this has a 100-gram mass at the end of it, and if I play it, you can see that when I pull it down and let go, the mass is going to oscillate. It's 100 grams. I put that there because I forget what it was. So I'm going to go ahead and pull it down. I actually have a stopwatch too, so I can find the time. Can you see that time? Let's see. I don't really do vertical videos usually, so I apologize. Okay, so we'll get to the actual time. Actually, let's record this time right first. I actually think I'm going to just scroll through here. And the second time I pull it works a little bit better. I'm going to pull it down and let it go, and let's go down. So right there, it's at, I'm going to write this as T1 is 8.2. And then let's do, it goes up, down, down. That's good enough. So that's 2. So T3, let's call it, is 10.53 seconds. Okay, so I can get the time it takes to oscillate up and down, but it is indeed oscillating. So we want to model this situation. I'm going to actually make more than one video on this. Today I'm just building a model for the force due to the spring and modeling that oscillation. And then the next video I'll animate it, and it's going to be so super great. Okay, so how do we get the force from a spring? Let me show you what we're going to do, and then we're going to do it. So if I have a mass hanging vertically and it's at rest and it's got some mass hanging from a spring, then I know that the net force has to be 0 because the acceleration is 0. If the net force is 0, then this spring force plus this gravitational force has to be equal to 0. So in the y direction, I can say Fs minus mg equals 0. This is just the y direction. So the force, the spring force, is going to be equal to the mass times gravity, where the gravitational field, where g is 9.8 newtons per kilogram. So what I can do is to add masses and record the position, because I'm suspecting that if you've ever played with the spring, the more you stretch it, the greater it pulls back. Also, if you have a compressive spring, the more you compress the spring, the more it pushes it back the other way. So this is Hooke's law, but we're gonna derive it numerically. We don't really even need to know that. So what I'm gonna do is to put different masses on here and record the mass and the position that it hangs at, and then we can get some data from that. So let's do it. Switching back to computer view, I'm going to now look at this. So I'm just going to scroll through here. So I have 20 grams hanging on there right there. That's 20 grams, and I put 20 in it, and I have a meter stick hanging up. Now, I didn't put 0 grams on there because I'm actually holding this up with a magnet, and if you do that, the whole thing messes up. So 20, we can now put a 50 on there, and that's 70 grams, and now 120 grams, and then 170 grams. And then I took all that off, and I put on, this is the distances, 78. So I actually have my meter stick down here, down at the bottom is 0, and the top is 100. And I don't really need to measure the stretch. I'm going to measure the position, and it's going to work. I think a lot of times people think, oh, it's a stretch of the spring. It doesn't really matter. So then I'm going to do that. These are recording the distances. So I have 78. You can barely see it. 46, 31.6. These are all in centimeters. And then I'm going to add 100 grams on there, and I write it as 120, but that's 100, and I get its distance, just so I have 5 data points. Okay, so now I have 5 data points. Okay, let's go ahead and, if I assume that the stretch is proportional to the force, I want to make a graph of force versus position. And if that's true, it should be a straight line, and the slope of that line will be my spring constant. So let's do that. This is Google Spreadsheets. I have nothing here. I'm going to write M in kilograms and y in meters. So now I'm just gonna copy down my data. So I have 20 grams at 0. Oh, you can't even see that. 0.02 at 0.783. It's on the board. I'm looking at it right there. Then I have 0.07. It is 0.627. The next one is 0.12. 0.529. No, 0.1. That was one I typed wrong. And then I have 0.12 at 0.465. I'm just recording the data. 0.17 at 0.316. Okay, so now the next thing I'm going to do is calculate the force. So up here, I'm going to call this the force in newtons. And it's just going to be equal to this value times 9.8. And then Google's pretty smart. It's like, hey, do you want to fill this in? So there I go. Now I have y and f. So let's highlight this. I'm not really good at graphing in spreadsheets, so insert chart, a chart. It is already the right kind of chart too. Okay. F versus N, that's fine. Set up axis series, switch rows. Where do you get the customize series? Trend line, and then the label is the equation. So there we go. So first of all, I mean, I know there's only 5 data points, and that's not that much, but it's still pretty cool, right? Because it's really linear. I did a terrible job. It was using a meter stick that taped to the wall and chalk. It wasn't even a great experiment. But still, it's a very linear slope of data. You could take more data for sure. But I get the slope up here is what I want. I'm going to write that down. So K equals 3.13 newtons per meter. And that's my spring constant. Don't worry about the intercept. We're going to deal with that later. So we found the model for the force of the spring. But the thing is, what's going to happen when I pull it down and let go? So let's talk about that. So first of all, I can write this F spring as K times Y. Do I need the intercept? I'm trying to think. I want to put that intercept in there. Let's say K times Y plus 2.65. Do I need that 2.65? I don't think I do. I should have put this at y equals 0. Okay, let's just do this just like this. Let's use that as my spring force. Who cares? It doesn't look like Cook's Law. Who cares? Okay. So now, why does it move like it does? Right? Let's think about that. So here I have my spring. And suppose I pull it down here. Right here it's at rest. So the two forces are equal. I pull it down and it's going to be a greater spring force pulling up than the gravitational force. I let go of that and what's going to happen? What's going to accelerate up? And it's going to start speeding up this way and moving up until it gets back to this position, at which point they're equal. But it's not going to stop because it's already moving. It was already moving in that way. So it's going to continue to move that way until it gets up to here. And this point, now the spring force is less than the gravitational force. So it's going to accelerate this way and eventually stop. And then start moving back down until it starts moving, oscillating back and forth. Okay, so how do we model this? Well, we can do this in one dimension. So I can do the following. I can say, start with my initial y. Y equals... actually, I'm looking at it right there. It's at 120 right now. So, no, it's at 100. No, it's at 52.9. So let's say y0 is, I pull it down to the 120 mark of 0.465 meters. I can calculate the force, F, and this is all just in one dimension. F is going to be equal to, so that's where I do need that y-intercept. So I'm going to use this. F equals negative ky plus 2.65. And I need that, right? This, because if I didn't have that, then it may or may not be positive or negative. This is just going to get things to work out the best. But that's the spring force, and then I have minus m times g. Now, we could deal with this in terms of acceleration or momentum. I feel like I usually do this in terms of acceleration. So that's going to be equal to m-a-y. So I can calculate the force in each. No. M-a sub y, the acceleration. So I can calculate the force. I know y, I know m, I know g, I know everything, I know k. Now once I know and I can use that to find the acceleration is going to be that force divided by my mass. Now I can use the definition of acceleration. Acceleration is defined as delta v, I'm in one dimension here, divided by delta t. It's going to be v2 minus v1 over delta t. So v2 is going to be equal to v1 plus a delta t. So if I break this into small time steps, and that's the key to all these numerical problems, then during a short time interval, I can assume the acceleration is constant, which it's not because it's going to be moving, but I can assume that. And if I know the starting velocity, which I do, v0 equals 0 meters per second, I can calculate the acceleration, pick a time interval, and find the new velocity. So let's say delta t equals 0.01. So I can do that. I can find the new velocity. I'll put it down here. v2 equals v1 plus a delta t. Now I can use the definition of average velocity, delta y over delta t, and I get y2 equals y1 plus v2 delta t. And here's another trick in that I'm using the velocity at the end of the time interval instead of the average velocity, and it turns out that that works fairly well. Then I can update the time, t2 equals t1 plus delta t, and then just go back up here and do it all again. So start off, calculate the force, calculate the acceleration, update the velocity, update the position, update time, do it again and again and again. And then we can graph that. Okay, so let's just do it first, and then we'll graph it, and then we'll compare that to the actual real data. So switching to computer, I am right here, trinket. Okay, so let's start off with some constants. So I'm going to say m equals 0.1, g equals 9.8. I'm not saying g is negative 9.8 because I've already assumed that it's going down. I don't need to say that again. I do need the initial y position. Y equals, I said that was 0.465. I do want to also add, I am modeling the motion of this with the spring force and with gravity. Normally, even in calculus-based physics, the idea would be to say, well, let's just ignore gravity for right now and make it oscillate because it's a lot easier to solve as a differential equation. We're adding gravity. Okay, we're going all out. We're modeling this the way we should. V equals 0. You'll notice two things. I don't put the units. If I do want to put those there as a comment, that's kilograms. Newtons per kilogram. Meters per second. And 2, I don't have subscripts, right? Because I'm going to actually change that value of y. I don't need to keep track of all the different y's. I'm just going to keep changing it. T equals 0, dt equals 0.01. Okay, k equals, what did I have? I already put it down, let's see. Negative 3.1. So k is 3.13. And then let's put f0. That's that spring constant. That's at 2.65. That's the y-intercept. Okay, let's just model this and see if it's working. So I'm going to first say while t is less than 2. So this will run it for 2 seconds. I don't need to put a rate statement in here because I'm not going to be animating anything, so I don't really need to do that. So the first thing I'm going to do, just like I said, is to calculate the force. F equals negative k times y plus f0 minus m times g. The acceleration a is going to be f divided by m. Now I can update the velocity. V equals v plus a times dt. Update the position. Y equals y plus v times dt. Update time. T equals t plus dt. Now, how do I know it's even done? At the end, let's just print out. Let's print the position and the time. Print t and y. Let's just see if it works. Let's run it. I should have saved it. Okay, it's giving something. It ran for 2 seconds, so that's good. Model spring mass. I don't know what I'm doing. That's a dumb name. Okay, so there we go. Now what I want to do is to actually graph the position as a function of time for that situation. So let's go over here and say g1 equals graph, x title equals time, t in seconds. Y title equals y in meters. Let's give it width equals 500. Height equals 250. Now I need to pick something to graph. F1 equals G curve. Color equals color.blue. Now down here, I just need to plot those data points. So I'm going to do it after the time, even though I think technically I should do it before the time, but it doesn't matter. So f1.plot t y, and let's run that thing. I mean, come on. That's pretty awesome. You know, this looks like a trig function. It is a trig function. We always talk about the solution of a mass on a spring is a trig function, but it's magic, right? There's no trig in my program. There's no pi in my program. There's nothing. But you still get it. I mean, it's not that complicated of a program. Okay, let's do this. I'm going to go up here and I'm going to say, I'm going to get rid of that. I'm going to say T, I'm going to do capital. Tap T OBS. Observational period, the time for one oscillation, is going to be equal to, I wrote this down, it's going to be 10.53 minus 8.2 divided by 2. That was 2 oscillations. Print TOBS equals TOBS in seconds. Okay, so that was a period of 1.165 seconds. So what's the period here? Well, if I look right here, I'm going to write this down. I have about a time of 0.55, and then all the way back over here, I get look at that, 1.68. So 1.68 minus 0.55 is going to be 1.13. I mean, that's a win right there. I mean, you just imagine the amazingness of this. Okay, look at this program. It's not that complicated, but I modeled the motion of a mass on a spring, and it agreed with reality. You know, solving that differential equation is not easy, but this is fairly straightforward. I mean, I hope you can appreciate the magnitude of what we've done here. It's huge, huge. Okay, let's do some other stuff. Let's play around with a little bit. We'll play around with a little bit more in the next video. What would happen if I make a smaller time step, a bigger time step of 0.1? Let's just see what happens. You'll notice that it's kind of blocky, but if I go right here, I get 0.49, 0.6. I'm still right around the same period, even though it's a terrible data. It works pretty well. Now, here's what doesn't work well. Let's change this to 0, and let's run this for a little bit longer, 4 seconds. What if I actually update the position and then update the velocity? So I'm going to switch the order of these, and it turns out that it doesn't work as well. There are different numerical methods that you can use. This is the first order Euler method, really, but I can do that, just making sure I have a velocity. Yep. Okay. And so there you see that it doesn't work as well, right? You'll notice something that shouldn't happen is that it starts oscillating at a larger and larger amplitude. However, if I go up here, 0.55, 0.69, it's still right around the right period. So that's pretty impressive. It's really kind of amazing that switching the order of those operations makes a big difference, but it really does. So if I'm going to put this, you want to do your higher order derivative stuff first. What did I do? I wanted to cut that. Cut it and put it up here. And then put it back the way I had it. And you see that's very well behaved. That's doing exactly what you'd expect. We could plot the energy of this, but I don't want to do that. I want you to be able to take the time and appreciate this code and see how beautiful it is, because it really is. It's the best thing. I will add this. You can plot a cosine function and see that it fits this. You could calculate the angular frequency for this and use that to actually find the value of pi. I've done that before. It's kind of fun to say, I can calculate pi just by using a mass and a spring and modeling this whole situation. And so there you did it. But okay, so I'm going to give you the code down below. The link to the rest of the playlist is down below for this whole series on learning Python and physics. But again, this is something that I do in class, and it's one of my favorite things to do, because you can do it in real time. You can collect data, you can make the graph, and everything is transparent so that they can see the magic of physics. Okay, so the next video we're going to do the same thing, but we're going to make an animation of this with VPython, GlowScript VPython. So I'll see you over in the next video whenever it comes out.